Okay, great. Thank you very much for the introduction and the invitation to speak. So what I talk about today is joint work with Frank Caligari, Toby G, and Vincent Poloni. And this is, in some sense, a continuation of Poloni's talk, although, in fact, the stuff from the last talk will only really show up maybe very close to the end. But so the motivation is exactly as in Vincent's talk, that we're interested in the modularity conjecture for abelian surfaces. And so just to state this very informally, there should be a bijection So maybe I should fix F a totally real field. There should be a bijection between certain L packets of cuspidal automorphic representations. For GSP4 over F. And certain abelian surfaces A over F up to isogeny. And so I guess Vincent already explained various ways to make this more precise. So for now, I won't really say much. Maybe I should make this a dotted arrow because we really don't know very much about this. So the first thing I want to do is sort of recall what we know. So, and I guess, so the point is that this should be such that the L function, so if you have a pi over here and a over here, this bijection should be characterized by the L function of pi is the L function of A. And so more precisely, this is the spin L function. So the degree 4L function for GSP4, and this is the L function of the first étale cohomology of A. So, well, I mean, the first thing is that unlike the case of elliptic curves, there is no analog of Eichler-Shimura. And so in the general case, namely, well, when the endomorphisms of A base change to F bar is just the integers, we really don't know much in either direction. So as I say, there's no analog of Eichler and Shimura, so we can't go from a modular form to an abelian surface. And, well, and the modularity conjecture, which is somehow the other direction, in this general case, all that are known at the moment are examples. So let me mention this work. So for F equals Q, finitely many examples of general A over F, or A over Q, which are modular, are known. So let me mention the kind of people who prove this sort of thing. So so this is a very computational subject. So basically what they do is, well, you find an abelian surface, maybe as the Jacobian of a genus 2 curve, and then you go and find the modular form, and then you have to prove that this holds. And in order to do that, they use the method of Faltings and Serre, which requires computing quite a few Hecke eigenvalues of this modular form, which is, well, for GSP4, this is, and in weight 2, this is extremely difficult computationally. So the people who do this, it's a long list. So this is the work of Brumer, Passetti, Tenaria, Poor, Voigt, and Yuan. So for instance, they've checked that there exists A over Q of conductor 277, which is modular. And it's of general type. And there's also work of Berger and Clausen, where they, in fact, they have a program for proving that certain abelian surfaces with a rational torsion point are modular, but they are at least capable of giving a sort of different method of proving that some particular abelian surface, I can't remember what its conductor is modular. And so I think that it's accurate to say that we only know that there are finitely many general modular abelian surfaces up to twist. And in all cases where one has been proven to be modular, it's been done by finding the modular form first. And this is done computationally. OK.
The smallest guy which is not correct.
And of GL2 type and of et cetera. So it's the smallest conductor of a general. Actually, maybe it's not actually. I don't actually remember. For some reason, though, they wanted to do this one first. OK. So, all right, but OK, so these are all kind of negative results, but we do have Galois representations. So, I mean, more specifically, with one of these L packets of the suitable type, we can construct a Galois representation rho pi. And of course, given an abelian surface, we can construct a Galois representation, say the Galois representation coming from the first state cohomology. And the idea is that the Galois we can't construct the abelian surface, but we can construct the Galois representation, which should be this Galois representation associated to the abelian surface. So, OK. All right, so before I state our main theorem, which is some sort of modularity lifting theorem, which is applicable in this situation, I want to discuss some applications. So the first thing we prove, sorry, this isn't really a theorem, is a potential modularity theorem. So if f is totally real, and A over f is an abelian surface, then A is potentially modular. Or in other words, there exists an extension f prime over f, probably non-solvable, such that A over f prime is modular. OK, and so a potential modularity theorem like this has some kind of standard consequences, which I'll now recall. So the first point is that this is actually good enough to get the L function LAS has a meromorphic continuation. To C and satisfies the expected functional equation. So how is this proved? So if you don't know this potential modularity business, the idea is to use a Brouwer induction argument and use Artin formalism for L functions. The L function of A over F is equal to some product of L functions for A over some extensions, F prime, raised to some integral power. So CIs are some integers, definitely possibly negative. And Fi is some intermediate extension between F and F prime, and such that it's solvable under F prime. And so base change theory will then imply that since A is modular over F prime, it's also modular over F.
There's a character twisted by a character.
Don't think I need to twist by any characters, but sorry, what am I screwed up?
I thought you needed LA tensor psi I over Fi s to the Ci.
I don't believe so. I mean, we write the trivial representation. I mean, assuming that F prime over F is Galois, we write the trivial representation as a linear combination of inductions of trivial representations. Of characters. Sorry, OK. So I'm told I need characters. Doesn't hurt. F on the left should be F prime, which? No, I really mean LA over F, the field we start with. So we don't prove it's modular, but we still prove the meromorphic continuation. OK? And of course, I mean, this is not really what you want, because this L function is supposed to be holomorphic. But without proving that it's actually modular, we probably have no chance of proving that. And another corollary is that if K over F is a quadratic extension, and E over K is an elliptic curve, then E is potentially modular. And OK, so the idea here is you just apply the theorem to the Weil restriction from K down to F of E, which is an abelian surface that the theorem applies to, and then use base change to get back to GL2 over this field K. And so, I mean, the interesting thing about this corollary is that K doesn't have to be CM. So let me just say, of course, if K is totally real, then this is an old result of Taylor's in the very first work on modularity, on potential modularity. And now if K is CM, or totally, let me say actually totally imaginary, this is a result, a much more recent result of the 10 authors, which I won't list because Patrick Allen will have to list them this afternoon. And this is a result in just last year, which is 2016, I believe. And now this is new if K is mixed signature. So for instance, if you happen to care about elliptic curves over something like the fourth root of Q adjoin the fourth root of 2, so then F would be Q adjoin the square root of 2, and then this is a field which has two real embeddings and a complex conjugate pair of complex embeddings. OK. So that's probably all I want to say about applications of the main theorem. Let me now state the main theorem. So I guess I shouldn't use these boards. So let me just go over here. So OK, so I tried to state our theorem precisely. So as usual, modularity lifting theorems have many hypotheses. So statement is a bit long. So
if you raise the board behind
Could I?
Raise the board.
Yes. Maybe. OK. So this is our main theorem. Let f be totally real. And we're going to have a prime p which is bigger than 2. And it's going to split completely in our totally real field f. And we're going to let rho be a Galois representation. Now satisfying, well, let's say unramified almost everywhere, such that the following conditions hold. So we're going to first of all ask, maybe I'll number or letter these, that this Galois representation has inverse cyclotomic multiplier. So by nu, I just mean the multiplier character from GSP4 to GM, and I'll write epsilon for the cyclotomic character. OK? That's not that much of a condition. And then B is going to be much more serious. We're going to ask that for every place dividing P of f, our Galois representation restricted to the decomposition group at V is ordinary with Hodge-Tate weights 0, 0, 1, 1, and residually p-distinguished. So I explain exactly what this means. i.e., there exists some alpha and beta p-adic units, and such that their reductions mod p are distinct. Such that, so some condition exactly like in Poloni's talk, the local representation is an extension of a two-dimensional unramified, so it has a two-dimensional unramified sub, and some extension. And since we have cyclotomic multiplier, we know what we have to put here. So just to explain the notation, I write lambda alpha for the unramified character which sends Frobenius to alpha. OK? So conditions A and B. C, we're going to ask that rho bar, the residual representation, is residually ordinarily modular. And what that means, there exists some pi, an automorphic representation of weight 2 which means that, well, it means that something about the infinitesimal character at the Archimedean place, which maybe, well, I'll be more concrete about what weight 2 means later. Such that rho bar is equal to rho pi bar, and rho pi satisfies A and B. OK? And now the last two conditions are kind of technical, so I won't say very much about them. So first of all, we need some kind of big image condition on the residual representation. So I'll just say that rho bar has big image, some condition used to pick Taylor-Wells primes. And finally, we ask that rho restricted to the decomposition group at some place V is pure for all V. So what pure means is essentially that this local representation satisfies the conclusion of the weight monodromy conjecture. If you don't know what that means, just doesn't even really matter. So, and then of course there's a conclusion. This is kind of important. Then rho is modular. Should not forget that. OK. So
pi and rho are living with?
Well, rho, I told you what it is.
Pi.
So pi is an automorphic representation for GSP4 of the sort that, at least at the Archimedean places, of the sort that we're kind of looking for. So that's actually very important. We're not allowed, I mean, there could also be that you're residually modular with some pi which is, say, cohomological, but that's not good enough for us. We really need it to be in weight 2. But OK.
That looks like quite a harsh condition.
Yeah. So in fact, this condition makes this modularity lifting theorem essentially useless, except for proving potential modularity. Yeah. OK. So in fact, I mean, since Steinach brought this up, I mean, it's actually reasonable to expect that if you have an abelian surface, and you look at least at a sufficiently large prime, there will be no modular forms of weight 2 and any level which are congruent to it. I mean, that's, I mean, I don't know if I'd put money on that, but it seems like that would happen 100% of the time. OK, so so now I get to make a bunch of remarks. It means something, but in particular, like if its image, if P is, I mean, if the image were something like GSP4 FP or FP to the n, it would be big. But I don't want to explain what it means.
But big implies irreducible?
Yeah. In particular, it will be irreducible. Oh, I should have said that, yeah. So our residual representation is always going to be irreducible. Yeah. OK. OK, so you should imagine that rho is exactly the Galois representation associated to an abelian surface. And so when would these conditions be satisfied? Well, if V divides P and A has good ordinary reduction, at V, and so if you look at A mod V and look at its sort of physical p torsion points, so to say that A has ordinary reduction, or good ordinary reduction at V means in particular it has good reduction, and this is actually a two-dimensional FP vector space. And we ask that, so Frobenius acts on it, and we ask that Frobenius has distinct eigenvalues. Then this condition B is satisfied for that B is satisfied. OK? And about this condition E, so condition E will always be satisfied in this case. E will be satisfied in this case. So you just don't have to worry about it, because we know that the weight monodromy conjecture is true for abelian surfaces, I guess by Weil and Grothendieck. OK, and now I want to make some remarks about some previous versions of this theorem. So Caligari-Garrity I guess announced in 2014 a theorem like this in the case that f is just the rationals and rho satisfies some strong condition on its ramification. So rho is sort of minimally ramified. And additionally, some annoying technical restriction. Which I'll say a little bit more later in the talk. And then Poloni gave a different proof, again with sort of these hypotheses, but he saw how to eliminate this annoying restriction. So, I mean, at least by the time this work started about a year ago, a little over a year ago, it seemed pretty reasonable that this theorem was within reach, but it wasn't still quite obvious how to prove it. And there's, well, as I'll try to explain, well, OK. So, and one more thing, which is that, I mean, which is related to this point about minimal ramification. Even if you only care about the case when f is the rational numbers, the first step is to extend f. So you'll wind up dealing with totally real fields anyways. And that's sort of as usual to deal with ramification, and in particular in order to use the so-called Ihara avoidance argument of Taylor's. So, because as we'll see, in some sense, this gets a little bit harder when f is not q. OK, so any questions about that? No? No? Hope I stated everything correctly. All right, so
Can you match up the conductors?
can we match up? Yeah, so in fact, at the end of the day, you get local global compatibility everywhere, which is actually not, yeah, OK. So not completely obvious, because for instance, if you just start with an automorphic form of weight 2, and you look at its Galois representation, you can't actually prove local global compatibility at, you can only prove it up to semi-simplification. But the point is that once you know that it's the Galois representation associated to an abelian surface, you know that the n has to be sort of maximal. So you do get local global compatibility. Yes, and you prove that the L functions are literally the same, not only up to finitely many places. Yeah. And so, I mean, that actually uses this hypothesis. OK. So I need to say something about how to prove this. So, I mean, before we deal with GSP4, it's a little bit helpful to recall the sort of antecedent to this theorem, which, as Vincent mentioned, is this work of Buzzard and Taylor. So what I want to now consider is, let's look at sort of analogous theorem for GL2 over Q. OK? And so the correct analog is not to look at weight 2 modular forms and elliptic curves, but to look at the correspondence between weight 1 modular forms and odd Artin representations. OK? So there's a theorem of Buzzard and Taylor, which looks a lot like our theorem, except in this situation. So what you're going to have is, so maybe I can't actually remember what I have to assume about P, so let's be on the safe side and assume it's not 3. So we're going to take a Galois representation. Well, probably not. Anyways, we're going to take a Galois representation a 2-dimensional Galois representation, and it's going to be irreducible. And we're going to assume, well, actually, it's going to be residually irreducible. So we're going to assume that rho bar, the residual representation, is irreducible and modular. And we're going to assume that some condition at P, namely, so rho restricted to GQP, is unramified and P distinguished. And all I mean by that is that it's unramified with Frobenius having distinct eigenvalues. So in the notation I had before, it's just a direct sum of 2 distinct unramified characters. OK? And then they prove then there exists weight 1 modular form F with such that rho is the Galois representation associated to F. OK? And actually, it's maybe worth saying with respect to Sarnak's question about what residual modularity means. Here, residual modularity really means something much weaker. It could mean modularity in regular weight. And that's because in this case, one has a sort of companion form in irregular weight results of Gross and Coleman-Volach. So, well, at least that's maybe one reason. Well, actually, maybe for the Buzzard. OK. Anyways, I already used this. So I want to say a little bit about what happens when you try to prove this theorem using the Taylor-Wiles method. So I hope will clarify what's sort of interesting when you're in irregular weight. And then I'll say a little bit about how Buzzard and Taylor proved this. And then I'll discuss another approach due to Caligari and Garrity. And so the reason I'm doing this is the kind of punchline is that, well, to prove our theorem, we can't really use the approach of Buzzard and Taylor. We also can't really use the approach of Caligari and Garrity. And so what we've actually done is found some kind of weird hybrid which manages to work and sort of avoids the difficulties of both methods for GSP4. So, OK? So now OK, so now I say some very basic things about attempting to prove a modularity lifting theorem for weight 1 modular forms. So, OK, so I mean, some of the issue, or the main issue, is that higher cohomology obstructs congruences. So let me give a very precise illustration of that. So if we let x be the modular curve, which I'll think about integrally, modular curve with level prime to p. And over x, we have our line bundle omega, which classical modular forms are sections of. So omega is nothing but the pullback along the identity section of omega 1 of E over x, where this is the universal generalized elliptic curve. And E is the identity section. So, OK, so I try to mention this in every talk I give. If you look at the exact sequence, omega to the k goes to omega to the k by multiplying by p. And you take coherent cohomology on x. What you see, starting with the sections of this, and the co-kernel is going to be the kernel of multiplication by p on the h1. OK, so I mean, literally, you have weight k modular forms. And you have weight k forms mod p, and you're trying to lift them. Weight k forms mod p. And if you try to lift them, the obstruction is exactly the p torsion in this h1. And so what's quite familiar is that when k is bigger than or equal to 2, this h1 vanishes. But when k is equal to 1, it really doesn't vanish. And so you can see this in various different ways. But one reason is just like when you study the cohomology of the Siegel threefold, as in Vincent's talk, the local representation at infinity, which you see when you have a weight 1 modular form, has an anti-holomorphic vector which contributes to this h1. But also, you could just see it via Serre duality, because this omega is essentially a square root of the canonical bundle. So k equals 1, we're really obstructed. OK, so now what do so this is bad because when you construct Taylor-Wallace systems, you construct a lot of congruences. And, well, we're saying that we can't construct a lot of congruences. So the idea of Buzzard and Taylor is that you get around this by working with p-adic modular forms. So I mean, one reason that this has higher cohomology is because x is proper. If x were affine, it wouldn't have h1. So what do Buzzard and Taylor do? They replace x by u inside the formal completion, or the p-adic completion of x, where u is just the ordinary locus. And now this is literally affine, or an affine formal scheme. OK? And what you can do is you can consider, so I apologize to people who know this story extremely well, but I mean, it's really important to understand it. So you consider, well, the space of p-adic modular forms, say in weight k or even just in weight 1. Now, of course, this is huge, because this is now an affine of positive dimension. But following Hida, we apply an ordinary projector. And now this is the finite dimensional space of ordinary p-adic modular forms. And the key point is it's unobstructed. Because there's no h1. I mean, to be honest, I don't think the reason people originally considered p-adic modular forms was to make weight 1 forms be unobstructed, but it's a perfectly good reason to do it. OK? So now, you can prove a modularity lifting theorem. What they do is they prove a modularity lifting theorem for ordinary p-adic modular forms of weight 1 rather than classical modular forms of weight 1. And so what they show is that rho is rho f for f in this space. Which is, of course, not what we want. Because so the next key thing to understand is that weight 1 p-adic modular forms are not necessarily classical. So f is a priori not classical. OK? And in fact, for a general p-adic modular form of weight 1, the Galois representation will look. So let's say that if f is an eigenform and with up eigenvalue f alpha, then the Galois representation at p will have an unramified sub with Frobenius eigenvalue alpha. But in general, you'll get a ramified extension. So something like this. And this thing will be not split in general. OK, but of course, we assumed that our Galois representation is really split. And thus, our modular form should really be modular. And now the idea is that, well, there should not just be a form f with up eigenvalue alpha. You're also having another unramified line with eigenvalue beta. So you should actually have two modular forms. So there exist two modular forms. F alpha, f beta, with up f star being star f star, where star is alpha or beta. OK? And now you do something which I'm not going to say too much about, which is you glue f alpha and f beta together. And so this, if you've seen this, this is where this sort of famous f is equal to alpha f alpha minus beta f beta over alpha minus beta thing shows up. And you show that this f is actually classical. And in fact, that will then imply that the f alpha and f beta are also classical. OK, so I don't exactly want to explain how this goes, but I want to explain something about it which makes it hard to generalize to GSP4. OK? So this is
Excuse me, pardon me for asking a historical question, but
yeah.
What is it in the assumptions which forces weight 1 here?
Unramified.
Unramified, I see.
And I guess you could really ask, what about oddness? So probably residually modular is forcing oddness, if you mean the right thing by residually modular. Yeah. OK, so now what's this thing I want to say? Well, f alpha and f beta are characterized by their Hecke eigenvalues. And for GL2, this actually determines their Q expansions. OK, and so in this Buzzard-Taylor gluing argument, where you write this thing down, you ultimately have to check that two p-adic modular forms are the same by checking that they have the same Q expansion. And so for GSP4, there is some completely analogous situation, which we'll see at the very end of the talk. We can get sort of analogs of f alpha and f beta, but we can't prove any relation between them a priori. I mean, for GL2, it's some exercise that since if these, say, have the same Hecke eigenvalues away from P, then all their prime to P Fourier coefficients are the same. So they basically have the same Q expansion. But for GSP4, the Q expansion is somehow coming from, not from, well, anyways, let me not say anything about that. But it's just completely not true that it's determined by Hecke eigenvalues. So this is like some big difficulty with the method of Buzzard-Taylor. OK. So now there's also the method. Where am I supposed to start? There's also the method of Caligari-Garrity. OK, and so I really can't explain this except at the most basic intuitive level. But the idea is, well, we want to construct Taylor-Wiles systems. If congruences of modular forms are obstructed, we're not getting enough modular forms to build our Taylor-Wiles system. But it turns out that there's also, in some sense, not enough Galois representations. And so if you can sort of match up the fact that there's not enough things on both sides, you can actually still make an argument. And so literally what you do is, well, there is this higher cohomology, and you need to remember it. So what they do is they build Taylor-Wiles systems. This is still in this GL2 case, out of something like the complex of R gamma omega. OK? So now let's return to the situation that we're in our main theorem. OK, so back to GSP4 over F. So Caligari-Garrity give us a strategy for proving the main theorem. And the problem, as I'll explain, is that we can't carry it out at the moment. So what we want to do, so we're back to GSP4. So now x will be as in Vincent's talk. So x is this Hilbert-Siegel-Schmür variety. which has dimension 3 times the degree of f. And it's a coarse moduli space of so-called abelian varieties of GSP4 type, well, of abelian varieties with an action of OF, and where A has dimension twice the degree of f. And again, we have some line bundle, little omega. So in fact, I'm only going to work in weight 2. So I don't need to introduce all the automorphic vector bundles as in von Slun's talk. We only work in parallel weight 2. So omega is a line bundle on X, which is the pullback along the identity section of, the determinant of the Hodge bundle. I guess it's the determinant of the Hodge bundle. So where A, again, is the universal 2 times degree f over q object, which doesn't actually exist. OK? And so Caligari-Garrity say that you should try So Caligari-Garrity say you can try to prove the theorem by patching this complex, which I'll give a name. So we really care about maybe sections of this line bundle. Those are the literal weight 2 modular forms, and I guess probably not. But we need to patch the whole complex, and maybe we also go ahead and localize at the maximal ideal of the Heck algebra, which corresponds to our residual representation in the theorem. OK? And so, well, they tell us we need to check some things. So we need Galois representations sort of including all the torsion classes that you see in the cohomology of this complex. You need local global compatibility at P, meaning these Galois representations satisfy the expected condition at P. This is this condition about having a 2-dimensional unramified sub. And maybe you need to know that, so as von Sant explained, in characteristic 0, this complex will definitely have cohomology in degree 0 all the way up through the degree of the extension. And at least as Caligari-Garrity wrote their argument, you want to know that C bullet is really perfect. Well, it is perfect, but you want to know it's supported in amplitudes 0 through the degree of f on q. OK? So what's known? Well, this is OK. But this is already a problem. It's OK for H naught. And this is by this doubling argument. But we have no idea for higher cohomology. And C, we just have basically no idea. So we can't carry out the method of Caligari-Gardy. So now I explain what we actually do.
You have no idea because of the possible torsion in H2, or is this something?
Why just H2? Or yeah. For B or C?
For C.
I mean, if you know how to prove it, let me know. OK, so
What's the question that would answer it? What's the thing we don't know?
don't know how to prove it. Yeah, OK. So now there's kind of a punchline here, which is that we're kind of OK when this degree is 1. OK when complex has length 2. And this is how Caligari-Gardy proved their theorem. Actually, literally what they did is they assumed C. And then B is OK. It's enough to only treat H naught by some argument with Euler characteristics, as Vincent explained. And then you're just OK. So the idea in general is that we should only try to prove R equals T theorems when there's cohomology in 2 degrees, and then use a p-adic gluing argument in general. So in the last couple of minutes, let me just basically say what the program is, and the details, well, we won't get into. So the idea is, so let's let SP be the set of primes above P, and let I inside SP be a subset. So now what you're going to do is on the Galois side, you're going to consider deformations where for V in I, you put this 2 unramified lines condition. And then whatever you have to put over there. And for V not in I, you put a weaker condition where you allow there to additionally be extensions between the 2 unramified characters. And then, OK. So we allow a ramified extension between the 2 characters. And then on the automorphic side, we consider one of these complexes, which Vincent didn't actually define, but I can quickly tell you what it should be. So you let xi inside the Hilbert-Siegel modular variety with Klingon level at P, or maybe it's p-adic completion. And you ask that, so this has a Klingon level structure is asking that you have a subgroup C inside, so you have a universal subgroup C inside inside the P torsion, and you ask that this be multiplicative. So so far this hasn't involved the set I, but then additionally for V not inside I, you also ask that the p-divisible group at V has p rank 2. OK? And so basically what you should imagine is we're mixing the two Hita theories in Poloni's talk. For the primes in I, we're doing the sort of irregular weight Hita theory. For the primes outside I, we're doing regular weight Hita theory. And this is sort of the guy where those families live. OK? If you'll permit me like 1 more minute, I'll just get to the punchline. So OK, so expect to be able to patch this complex, which is the cohomology of xi of omega squared. And now this has amplitude between 0 and the size of the set I. And for technical reasons related to the technical reasons that obstruct us in Caligari-Garrity's strategy, we can only do this when I is equal to 1. But then the miracle is that the output is enough to make a gluing argument work. OK, I was hoping to say a little bit more about that. I'm sorry I didn't and ran out of time. But this is somehow the idea. So neither strategy works. But by just running Caligari-Garrity in the case where there's cohomology in 2 degrees, there's, of course, supposed to be an ordinary projector here. Otherwise, this thing is some enormous garbage. Yeah. And that's the idea. OK.